everyone, welcome to Diksha Karnataka YouTube channel. I know that those who are preparing for KCET may be ignoring COMEDK for now, and then last few days they will jump together and say that we need content for COMEDK. So that's why we started our COMEDK series. I know some of you are exclusively preparing for COMEDK are watching this, but those who are preparing for KCET exam are ignoring it. But do not ignore it, because if you really want to appear for COMEDK exam, the questions are tricky. They are intelligent question, not like KCET, and sometimes it might be difficult for you if you are not prepared. So that's why we are going to discuss all the important questions and the pattern that we are discovering by solving those questions. So today is time for us to discuss electromagnetic induction, alternating current and EM waves together. Now out of this, alternating current is very important chapter. The questions that generally do not come in KCET do come in COMEDK. So let's see one by one. So let's start with our session. First question: there are two coils A and B as shown in the figure. A current starts flowing in B as shown when A is moved towards B, and stops when A stops moving. The current in A is counterclockwise. B is kept stationary when A moves. We can infer that. Now here in this question, where you see that A is basically the current in A is counterclockwise, so that is given information in the question. Counterclockwise means in this direction, okay? And also if you see that in the diagram itself, there is a current shown in the B ring as well. Now if you really want to solve it, that can be tricky, but here if you see that what is the direction of current in B, direction of current in B is also counterclockwise, okay? So direction of current in A is counterclockwise, direction of current in B is also counterclockwise. Now if you read the option carefully, so this is an intelligent question. If you think, oh, how to solve this question, you will be confused, but if you see the question, if you read the question properly, if you see the image properly, you will realize that there is only one option where there is a constant current in the counterclockwise direction of A. Okay, so that is the answer for this question. Now if suppose the same question is asked without this arrow, how to find that also I will tell you. That here suppose that the current is counterclockwise, so what is the magnetic field due to this loop? So magnetic field due to loop is out of the loop, so it will go like this. Magnetic field lines will go like this, so it will come out and it will go in. Okay, so it is so inside the loop it is. So how to draw that? So inside the loop the magnetic field lines are out of the loop. So here this is the counterclockwise current, so here it will be out of the loop. Okay, and whatever is going out, they will come back in a circular way. Okay, so there is if you consider a straight line, okay, straight line carrying current, the magnetic field lines are always circular, right? And based on the direction of current, so if this is the direction of current, the lines are circular. Same law is applicable for a circular loop as well. So if a circular loop carrying current, okay, inside the loop the magnetic field is out of the paper, so that means it is going out of the paper and it is going into the paper when it is outside. So outside the loop the magnetic field is into the paper. Remember always, whenever you are considering any kind of loop, okay, how to find the direction of magnetic field due to a loop, curl your fingers in the direction of current, then your thumb will point towards the magnetic field. Okay, so this is the inside the loop. Outside the loop it will be exactly opposite, because whatever lines are exiting, the same line has to go back. Okay, whatever lines are coming out of the page, where they will go, they cannot go infinity. Okay, magnetic field lines are always closed loop. So that means it's a three-dimensional figure, slightly complicated to imagine, but you should imagine like this, that if a line is coming out, the line has to rotate and it has to go back. Okay, so that means the field lines, so whatever is coming out of the loop from inside, okay, into the page is out of the page is denoted by this, So out of the page it is into the paper. So that means whenever you go out of the loop, it will always be into the page of the paper, and it is not constant, it is varying. Okay, it is varying. Magnetic field is varying, but the speed of the current, speed of the loop is constant. That means when it is moving towards this closed loop, what happens is that the rate of change of magnetic flux associated with this loop remains constant. So if the speed is constant, remember always, whenever there is a speed involved and this loop is stationary, that means the rate of change of flux linked with this external coil will always be constant. Okay, so initially a small number of lines are passing, but as the line number increases, but the rate also increases. Okay, so rate remains constant. Okay, so rate of change of flux remains constant. Now as the rate remains constant, what will happen in the loop? Let us understand that. So this loop will induce a current that opposes the cause. Now what is the cause that inducing the current? The cause is a magnetic field which is into the paper. A magnetic field into the paper. Okay, so into the paper means it will induce an EMF which will oppose it. That means the induced EMF will give a current which is out of the paper. Induced EMF always opposes the cause. Here magnetic field lines are increasing, that means magnetic field lines are changing. Rate is constant, but there is a change, so that means it will produce an EMF, and that will oppose the cause. That means the induced EMF will have a current which is also out of the paper. So if this is out of the paper, this will also be out of the paper. Remember that this is a shortcut. If you see similar questions in the exam, that induced EMF in a coil, generally two coils are linked such a way that if one coil is out of the paper, the other coil will also have out of the paper. So if this is counterclockwise, this will also be counterclockwise. Okay, now because the motion is constant, the rate of change is constant, that means the EMF will also be constant. And there is one more hint given in the question, that as soon as you stop the motion of the coil A, the induced EMF becomes 0. That means if in case the current is varying, then it would not come to 0 immediately, it would have taken some time. Okay, clear? So that's why the answer is D. Now in this particular question, as I mentioned, the arrow sign is already given. So read the question before answering. If your question have given you hint, use that hint and answer fast. Okay, answering fast is very, very important. A coil has 1000 turns and 500 centimeter square as its area. The plane of the coil is placed perpendicular to a uniform magnetic field of B is equal to 2 into 10 to the power of minus 5 Tesla. The coil rotated through 180 degrees in 0.2 seconds. The average EMF induced in the coil in millivolt is. So first of all, the coil number of turns is given. Okay, area is given, magnetic field is given. Okay, so first of all, suppose this is the coil, it has an area. Okay, some field lines are crossing it. So what is the flux link? First step is to calculate the flux link. So what is the magnetic flux linked with the coil? Magnetic flux linked with the coil is given by number of turns, area into magnetic field. Okay, and because it's initially perpendicular means, remember, for magnetic field, okay, you don't need to consider any other, the cos theta component will be 1. Okay, now that means what is the n? N is given 1000, area is given 500 centimeter square. 500 centimeter square means 10 to the power of minus 6. Okay, no, minus 4. Okay, 1 centimeter is equals to 10 to the power of minus 2 meter. So square means square of both things, so it will be 10 to the power of minus 4. Don't forget to convert centimeter to meter. Okay, you have to do that because there is a square, so conversion factor will also be squared. That's why 10 to the power of minus 4. Now what is the magnetic field? Magnetic field is 2 into 10 to the power of minus 5. Okay, now let's simplify. Now how many zeros we can cancel? 1, 2, 3, 4, 5. So all these zeros can be cancelled against this number. So what we have? We have 5 into 2 into 10 to the power of minus 4. Okay, 1, 2, 3, 4, 5. 5 zeros. 5 zeros means 10 to the power of 5. So 10 to the power of 5, 10 to the power of minus 5 will be giving you 10 to the power of 0. Any number to the power of 0 is 1. So that means this number goes away. So now we are left with 10 into 10 to the power of minus 4, that is 10 to the power of minus 3. Okay, Weber. So this is the flux linked with the coil. Now when you rotate it by an angle of 90 degrees, when you rotate the coil by an angle of 90 degrees, the change in flux is from phi to 0. Change in flux is phi to 0, that is angle 90 degrees. Okay, so this is the change of flux. So this is the flux linked when the loop is stationary. Now if you rotate it by an angle 90 degree, okay, when the angle becomes 90 degree, the flux, whatever flux linked, will completely be 0. Okay, so so basically what you have done, you have just rotated it like this. Okay, so change in flux will be 90 degrees. Now when you change the angle another 90 degrees, that is 180 degrees, the flux will be minus phi. Okay, phi to minus phi. So total change in flux from by 180 degree rotation, okay, the flux change is phi to minus phi. So what is the total flux change? Total flux change is given by minus phi minus phi. Okay, so basically final minus initial is the change in flux. So change in flux is minus 2 phi. Now what is the induced EMF? Induced EMF is minus d phi by dt. That is minus 2 phi divided by 0.2. That is minus cancels and we get 10 phi. Okay, 10 phi is the induced EMF. Now what is the phi? Phi value is given here, 10 into 10 to the power of minus 3, that is 10 millivolt. So the induced EMF is 10 millivolt. So as I said, the questions are not super easy. Okay, this part maybe you have figured out. This part is very tricky. That rotating a loop by angle 180 degree refers to a change in flux to equals to 2 phi. Okay, minus I have used, minus sign you can ignore if you want, but so rotating a loop by angle 180 degree refers to a change in flux by 2 phi. So whatever flux linked when the loop is stationary, if you rotate it 90 degrees, the flux, all the field lines are passing perpendicular, that means no field lines are passing through it, so the flux linked will be 0. But when it rotates opposite side, so this side was phi, now this side it will be minus phi, so total change in flux will be 2 phi. Okay, so this is the trick, this is the understanding that you have to have. Now another intelligent question. Figure shows a circuit that contains 3 identical resistors with resistance 9 ohm. Okay, each 2 identical inductors with inductance L equals to 2 millihenry each, and ideal battery with epsilon equals to 18 volt. The current I through the battery just after switch is closed is. So now you might say, sir, this is a DC circuit, it contains R, L and C. We have not studied R, L, C in DC circuit. Yes, you have the basic idea. It is not a LCR DC circuit. It is actually a simpler problem from electromagnetic induction and some capacitance concept as well. Okay, so what is the concept here? They have asked you just after the switch closed in. So remember 2 things. When you are using a battery, that is a DC battery with inductor, it behaves differently than what it does in AC. In AC you calculate the impedance, then you calculate the current. Here it is not like that. So here you have to remember 2 conditions. Okay, for inductor Okay, when you just switch on the circuit, what happens? The inductor immediately induces an EMF in the opposite direction and stops all flow of current through it. Okay, so just after the circuit is switched on, that is at t equals to 0, okay, the resistance of an inductor is infinite. Resistance of an inductor is infinite. Okay, that means it does not allow any current through it. But as the time increases, the current, the magnetic flux linked with the coil becomes constant, and because it becomes constant with time, okay, t is equal to high time. If the t becomes, if you let it sit through for a long time, say infinity, okay, not infinity, high, very high value, for after a long time, actually it is a long time, okay, as the magnetic flux slowly becomes constant, the resistance of inductor becomes 0. So initially, just after the circuit is switched on, it gives an infinite resistance, but with time it gives you a very low resistance, that is 0 resistance. Okay, exactly opposite happens for capacitor. For capacitor, exactly opposite happens. So what happens for a capacitor? As soon as you switch on the circuit, it starts charging. So that means it offers 0 resistance. Okay, because the capacitor is charging, it offers 0 resistance. But with the long time, okay, as the time increases, okay, with the long time, what happens is that the capacitor is fully charged, so it is full. Now it will not be able to eat anything. So what it will do? No, I don't want anything. So it will offer a infinite resistance. Okay, so capacitor and inductor are exactly opposite. In DC circuit, capacitor at exactly after switching on the circuit, the inductor gives you an infinite resistance, whereas capacitor gives you a 0 resistance. And after a long time, the inductor gives you a 0 resistance, capacitor gives you an infinite resistance. Okay, so let's do that. Here the question is just after switching. So just after switching, this inductor will be closed for any current, so it will not allow any current to pass through it. So it will basically behave like an open circuit. Okay, it will behave like an open circuit. If the same question is asked with an infinite after a long time, then you just simply need to draw a straight line. So that will be a connector. Okay, otherwise there will be no current passing through it. Okay, so exactly after the circuit is switched on, this inductor is off, this inductor is off, so no current passes through this. Okay, no current passes through this, inductors are off, that means they are disconnected from the circuit. Okay, and effectively disconnected. And what will happen to this capacitor? This capacitor will be simply be joined. Okay, so that means now we can simplify the circuit. So if you see that here we have this resistance is no longer part of the circuit because it is disconnected. This resistor is disconnected, no current can pass through this light. There is a bridge, but the bridge is not there. That means no current can pass through this. Only this resistor and this resistor are connected, and they are connected in parallel. So what is the equivalent resistance? The equivalent resistance when two equal resistances are connected in parallel is R by 2. Okay, two equal resistances connected in parallel, the equivalent resistance is R by 2. If two equal resistances connected in series, equivalent resistance is 2R. When they are connected in parallel, it is R by 2. So R by 2 we have calculated. The EMF is given. So what is the current in the circuit? So current in the circuit is EMF divided by R by 2. That is 2 EMF by R. Now let's put the values. 2 into EMF here is given 18 volt, and the resistance is given as 9 ohm. So 9 to the 18, so it will be 4 ampere. So current in the circuit is 4 ampere. Okay, so just if you understand this concept, then this is a very easy simple concept. Okay, but as I mentioned that COMEDK questions are slightly intelligent, so you have to apply that intelligence and solve the questions. The equivalent inductance of two inductors is 2.4 Henry when connected in parallel, and 10 Henry when connected in series. What is the value of inductances of the individual inductors? Now this is a same question can be asked using capacitors. You have not capacitors. You have solved similar questions using resistors in your class 10th. Okay, two resistors are connected in parallel, two resistors are connected in series. So inductors are exactly like resistors. Okay, unlike capacitors, inductors are exactly like capacitors. So in series, what happens? So what happens is that, first of all, equivalent inductance in parallel is actually L1 L2 by L1 plus L2, and series is given by L1 plus L2. This is given 2.4. This is given 10. Now will we solve it? No, we will not solve it. You can solve it, no problem. L1 L2 is 24, then you take L1 L2, you will get a quadratic equation, you can solve it. Because we are solving multiple choice question, we will not do that way. First of all, we will see that any of them, if you add these two, are we getting 10? 8 plus 2 10, 6 plus 4 10, 5 plus 5 10, 7 plus 3 is also 10. So this condition is satisfied by all four combination. But what about this one? So we will do the back calculation method, that is much faster. So if you multiply these two quantities, it should be multiplier of 24. Okay, so 8 2s are 16, which is not very close to 24. 6 4s are 24. 6 4s are 24 divided by 10 is 2.4, right? So basically we can say this is our answer. If you want a little bit more detail, you can say that, okay, L parallel is equals to L1 L2 divided by this 10, right? This value is known. So L1 plus L2 is there in the division, so 2.4. So L1 L2 equals to 24. Okay, this is same as resistances. Okay, two resistors connected in parallel, R1 R2 by R1 plus R2. Same formula is applicable for capacitances as well. But here we are little smarter now. We have grown up. We are not going to use the method that we are using in our class 10th. Okay, so we will be using back calculation method. So if we multiply, if we add them, we get 10. If we multiply them, we get 24. There is only one possible combination. 6 4s are 24. Now if they give you, say, option 12 comma 2, 12 plus 12 into 2 will give you 24, but if you add them, it will give you 14. So that is not matching with 10. Okay, so remember that addition is 10, multiplication should be 24. That's how we solve, right? Now let's move on to the next question. A 1 meter long metallic rod is rotated with an angular frequency of 400 radian per second about an axis normal to the rod passing through its one end. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. The EMF developed across the end of the rod is. So there is a theory, the derivation you can do. I am not doing it. Suppose there is a rod which is rotating around some axis, and there is a magnetic field. The length is L. Okay, actually not, rod is not like this. Suppose this is an axis and a rod is rotating in a magnetic field, okay, with an angular speed of omega. Then what happens through this rod? There is an induced EMF. Okay, that induced EMF is obviously the length of the rod is L. Okay, when the rod rotates in a magnetic field in an angular velocity, okay, there is an induced EMF. That induced EMF is given by half B omega square L. Okay, this can be proven. Okay, there has to, you have to do the integration and calculate it, but we are not doing it. We can simply say that this is the value, so half into B is 0.5 omega square. The formula is there in your NCERT book. If you want, you can check that. So this speed is 400 square and length is 1 meter. Right, so let's simplify. Sorry, there is it is not omega square, it is simply omega. Okay, square will not be there. B omega L. okay, B omega L. So now let's simplify. So you will get 0.5 into 400 is 200, so 200 by 2, which is 100 volt. So the induced EMF is 100 volt. Okay, so this question came in 2024. The formula is there in your textbook, and this formula came once in KCET. If someone is preparing for KCET, the same formula was asked in KCET once. Okay, so this is 100 volt is the EMF. Now next question, a coil is placed in a magnetic field B as shown. So here is a coil placed in a magnetic field, and there is an induced current. So induced current direction is also shown over here. A current is induced in the coil B because B is outward and decreasing parallel to the plane, obviously not possible. So first of all, basically they are asking you about the magnetic field B. Okay, they are asking you about the magnetic field B. Induced current is in this direction, so in this direction means the induced magnetic field is outward. So induced magnetic field, first what is given here, induced magnetic field is given. So induced magnetic field is outward. Outward means dot with a circle. Dot with a circle represents outward. Okay, inside. Okay, magnetic field is inside, right? So we have to compare it with the inside magnetic field only. Now induced magnetic field is outward. So what can be the original magnetic field? Original magnetic field can be, there are two possibilities. Either the original magnetic field is into the page of the paper, okay, that is inward and increasing. It can be inward and increasing. So B can be inward and increasing, so that the opposing magnetic field is outward, or B can be inward but decreasing. B can be outward and decreasing. If original B is outward but it is decreasing, then induced EMF will say no, don't decrease, I will help you. So it will induce an EMF in the same direction. But if the magnetic field is stronger, say I am the boss, I am increasing, then the induced EMF will say no, I will decrease you. So that is how induced EMF work. Okay, so when the magnetic field is increasing, it exactly opposes the magnetic field. If the magnetic field is decreasing, then it helps and increases the magnetic field by producing magnetic field in the same direction. This is the main concept, that if magnetic field is increasing, induced EMF will be opposite. If the magnetic field is decreasing, induced EMF will be in the same direction. So either it will be inward and increasing, or outward or decreasing. Let's see. So outward and increasing. Outward and increasing is a long combination. Okay, if it is outward, then it has to be decreasing. So outward and increasing is wrong. Outward and decreasing is correct. Outward and decreasing is correct. Okay, parallel. If the magnetic field is parallel, induced, there is no linkage with the magnetic field and flux. Magnetic flux link will be 0. So it will be only outward and decreasing. Outward and decreasing is the correct option. Understand this, magnetic field increases, induced EMF opposes it. Magnetic field decreases, induced EMF supports it. Okay, so it's like a bank. If you have a very high money, it will tax you, but if you have low money, it will help you by giving you money, like that. Okay, now let's move on to the next question. The variation of induced EMF epsilon with time t in a coil, if a short bar magnet is moved along its axis with a constant velocity, is best represented as. So here we have a magnet which is pushed into the coil, and as it is pushed into the coil, what happens is that what will happen to the induced EMF. Now let us understand this. So when the magnet is coming towards the coil, now obviously the polarity is not mentioned, so we will not know what will be the direction of the induced EMF, but what we will know that as the magnet is approaching the coil, okay, the induced EMF will slowly increase. Okay, induced EMF will slowly increase. Okay, when the magnet is completely inside the coil, okay, so magnetic field will be 0. And again when it is exiting the magnet coil, okay, the magnetic the current will again increase, but in the opposite direction. Okay, so magnetic field will be, suppose this way, when it is coming this way, okay, the magnetic field, the induced EMF is positive, suppose. Okay, we do not know, suppose when it is approaching it is positive, then when it is leaving it must be negative, or vice versa. We do not know whether it is positive or negative initially. Okay, so the magnetic field has to be, one case it will be positive, other case it will be negative. That much we know. So if you see that here magnetic field is increasing, decreasing, but here both cases it is positive. Okay, so this is not possible. Here magnetic field is positive, negative initially and positive later on. So basically when it is approaching it says that the induced EMF is negative, and when it is exiting it will be positive. So this is actually matching with our assumption that with our understanding that magnetic field induced EMF cannot be positive in both cases. It has to be positive. If it is positive here, it will be negative here. If it is negative here, it will be positive over here. How do we say positive or negative? Based on the direction of current. Okay, so we take one direction as positive, the other direction will be negative. Okay, based on the direction of current we say that whether the magnet is moving into the coil is positive or negative. So here and all other cases magnetic induced EMF is always positive. Only one case induced EMF is positive and negative both, so that is the correct answer. So the pattern is the induced EMF slowly increases, then it reaches a peak value and then slowly decreases, then it becomes 0. When the entire magnet is inside the coil, the induced EMF will be 0, and again when it is start leaving, the induced EMF will be slowly increasing and then falling, and when the magnet is far away the induced EMF becomes 0. Okay, that is how the induced EMF works, right? Now next question. A parallel plate capacitor of capacitance 20 microfarad is being charged by a voltage source whose potential is changing at the rate of 3 volt per second. The conduction current through the connecting wires and the displacement current through the plates of the capacitor would be respectively. So first of all, a parallel plate capacitor of capacitance 20 microfarad is being charged. That means it is charging. The capacitor is charging. It is not fully charged. Okay, that means it is being charged, and the change in potential is also given 3 volt per second. That means conduction current and displacement current both has to be same. Okay, according to the Maxwell's law, conduction current has to be same as displacement current. Okay, there is no other way. So conduction current and displacement current both has to be same. That means, and they are not 0. Okay, they are not 0. So if you see that combination 0 0 0 60 60 0 is not possible, so only one case it is possible, which is 60 microampere and 60 microampere. Now if they give you another combination, suppose they give 20 microampere and 20 microampere, then how you will know that which combination is correct? Okay, if you see this kind of question, you don't need to do any mathematics. You simply see that capacitor is charging. That means the current is not 0. Okay, current is not 0. If the capacitor is fully charged, both currents will be 0. If capacitor is fully charged, both current will be 0. But if here the capacitor is not fully charged, it is being charged, that means both current has to be same and not 0. So that means this will be the correct combination. But in the exam, suppose they give you the same question. Okay, this is an easy question. Okay, this is from electromagnetic wave. Without solving also you can solve it. But if they give you a different order, then how do you know that whether this is correct or that correct? For that you have to use the capacitance problem. Q is equal to CV, okay, or dq by dt. This is the charge that is being stored in the capacitor. Dq by dt, that is the current, displacement current, is given by C into dV by dt. Okay, so capacitance is given 20 microfarad, 20 into 10 to the power of minus 6, and capacitor, the voltage is changing by the rate of 3 volt per second. That means dV by dt is, so dV by dt is 3 volt per second. Very easy formula, just multiply it, you will get 60 into 10 to the power of minus 6, that is 60 micro ampere. Okay, so the current, the displacement current is 60 microampere, so the conduction current by default will be always equals to displacement current, so this will also be 60 microampere. Conduction current and displacement current will always be equal. Okay, there will be no case that conduction current and displacement current are different, they will always be equal, remember that. Now, next, the electric field associated with an electromagnetic wave in vacuum is given by E is equal to 40 cos kz minus 6 into 10 to the power of 8 T I cap, where E, Z and T are volt per meter, meter per second respectively. The value of wave vector k is. So basically they are asking you what is the value of this k. What a difficult question. Okay, so what is the standard equation of a wave? Standard equation of wave, this can be electromagnetic wave, this can be any wave. Remember that it is always given by A sine, okay, omega t minus k x, kx, ky, kz. Okay, here it is propagating along z axis, so that's why it is given. Okay, so and there can be a positive negative sign altercation as well, so here it is given as kz. So here what happens is that the direction of propagation is along the negative x axis, that's why they have interchanged the negative positive sign. So negative positive sign does not matter as long as you see that anything with the time actually gives you the omega. Anything with the coordinate system x, y, z gives you the wave vector k. Okay, so if you compare this and this, you will see that omega is actually equals to minus 6 into 10 to the power of 8, but we will not take the minus. As I mentioned, minus only changes the direction of the wave, otherwise this is the standard wave equation. So omega is 6 into 10 to the power of 8. Now what is the relationship between omega and wave vector? So wave vector k is given by omega by c. There is also one more formula that k is actually equals to 2 pi by lambda. So you can use this formula to calculate wavelength lambda, or you can use this formula to calculate the wave vector itself. Now omega is given 6 into 10 to the power of 8, c is given 3 into 10 to the power of 8. We know that, not given, we know that, so the value of wave vector is 2. Okay, so 2 per meter. Okay, wave vector, because it's z is in meter, so it's a dimensionless quantity, so it has to be per meter. Okay, 2 per meter is the correct answer. So remember this formula, it is very handy. An electromagnetic wave is transmitting energy in the negative z direction. At a certain point and certain time, the direction of the electric field of the wave is along positive y direction. Okay, so direction of electric field of the wave is along positive y direction. What will be the direction of the magnetic field of the wave at that instant? Okay, so electromagnetic wave is transporting energy in the negative z direction. So electromagnetic wave is along negative z direction, so negative k cap. Electromagnetic wave is negative k cap. Electric field vector, it says that it is along the positive y direction, so it is positive y direction. Y direction means j cap. Okay, you have to find the direction of magnetic field. Magnetic field will be either, now magnetic field and electric field are always perpendicular to each other, so it will be either positive I cap or negative I cap. That is positive x direction or negative x direction. Now we have to find what it is. Okay, how to find that? Remember one thing, that electromagnetic wave, the direction of electromagnetic wave given by E cross B. Okay, electric field cross B gives you direction of electromagnetic wave. This is very simple vector geometry problem. Okay, it is not a physics problem. Only thing you need to know that electromagnetic wave is E cross B. Okay, so E is given minus k cap, Okay, E is given plus j cap. So what we will cross with it to get this minus k cap. So how to do that? So in cross product you need to remember I, j, k. Okay, in circular order, in this order. So if you do I cross j, you get k. If you do j cross k, you get I. Okay, if you do k cross I, you get j. Now what we are trying to find? We are trying to find k cap. We are trying to find k cap, not k cap, but minus k cap. We are trying to find minus k cap. J is positive. So j, I cross j is k cap. So j cross I must be giving you minus k cap. Okay, I cross j is positive. So j cross I should be minus k cap. So here it will be simply I cap. J cross I cap. J cross I, that is opposite to that circular motion. So j cross I will only give you minus k cap. So it will be along the positive x direction. It will be along the positive x direction. So first thing first, electromagnetic wave, electric field, magnetic field, all are mutually perpendicular. So x, y, z, all three directions are involved. Okay, if EM wave is along z direction, E and B must be along x and y direction, positive, negative, based on the direction of propagation. So here electromagnetic wave is given minus k cap, E is given j cap. E cross B will give you the direction, right? Now in case, suppose in case you find out that it is how to suppose the electric field was given, I cap. Okay, electric field was given I cap. Now what you are trying to find? You are trying to find minus k cap. Now I cross j will give you plus k cap. I cross j will give you plus k cap, right? So now how can you make this minus? To make it minus, you must have to make this minus. Okay, to make this minus, you must have to make this minus. So if electric field is along positive x direction, magnetic field will be minus y direction, negative y direction. Okay, so just remember that how to first you figure out the what is the combination, and once you have figured out the combination, then just find the direction. That is sufficient. Okay, now next question. In the series LCR circuit shown, the impedance is, so basically very simple question. Series LCR circuit is given, voltage is given, frequency is given, they ask you impedance. Okay, how to calculate impedance? Very easy. XL equals to 2 pi F into L, and generally in competitive exam they will not give you simple 50 Hz or like that. They will give you enough value to calculate without using a calculator as much as possible. Okay, so it will be 2 pi by 50 by pi into L is 1 Henry. So pi cancels and you get XL equals to 100. Okay, XL equals to 100. What about XC? XC is 1 by 2 pi FC, 1 by 2 pi F into C. So that is 1 by 2 pi into 50 by pi into C is 20 microfarad. Micro means 10 to the power of minus 6. So pi cancels. 2 5s are 100. 100 into 20 is 2000. So 10 to the power of 6 by 2000. Right? 2 into 50, 100. 100 into 20, 2000. Don't make mistakes in the calculations. Okay? So 10 to the power of, so XC is 10 to the power of 3 by 2. 3 zeros cancel from the bottom, 3 zeros, 10 to the power of 6. So it will be 500. Okay, so 10 to the power of 3 means 1000. 1000 by 2 means 5000. Now let us calculate the impedance. Impedance is square root of R square plus XL minus XC whole square. Okay, R given here 300. So 300 square plus 100 minus 500 square, that is 300 square plus 400 square root, that is 500. 3 square plus 4 square is 5. 3 square plus 4 square root is 5. So 300 square plus 400 square root will be 500. Now next question. Figure shows a series LCR circuit with R equals to 200 ohm and C equals to 15 microfarad and L equals to 230 millihenry. If EMF E is equal to 36 sine 120 pi t, the amplitude I of the current I in the circuit is. So amplitude capital I of the current I in the circuit is close to. So they ask you to calculate the current. The similar question was asked in your final board exam, where what you have done to calculate the amplitude, you have done I is equal to V by R. Actually it is not correct. You have to find the impedance to calculate the current. How to find the impedance? Again same method. XL is equal to omega L. Here omega is given. Okay, so if equation is given, any equation is given like this, okay, remember that that means it is omega. Okay. Okay. Let's see. So omega is given here. So EMF equals to A sine omega t. Okay, so this is omega. Omega is 120 pi. So put that value. 120 pi into L is 230. This is a bad problem in my opinion. Okay, because you require a calculator to solve this, and that will be turning out to be 1020 minus 1, 23. 23 into 120, which will be okay, let's see, 336. So you will get some value. 23 into 12, 46, 23, 276 into pi, that is 3. That will be 18.8. 21 and 6 plus 2 8, right? 818, approximately 818. Have I done it correctly? Let me check once more. 230 plus 46, 276. 276 means 600 plus 210. Yes. Okay, so into 10 to the power of minus 1, so that is 81.8. so this is the value of XL. Okay, what is XC? XC is 1 by omega C, that is 1 by 120 pi. You cannot help it. You have to use the on-screen calculator to calculate such questions. Okay, again C is 15 microfarad. 15 microfarad means 10 to the power of minus 6. Okay, so 10 to the power of 6 divided by 15, 150 into 30, 180. Okay, 15 into 12 is 180. So 180, and there is one more 0 into pi. So it will be 10 to the power of 4 divided by 18 pi, and obviously this is not a circuit, is in resonance. You have to after calculating this, you have to calculate Z. Z is given by square root of R square plus XL minus XC square. Okay, which will come out approximately to 116 ohm. Okay, R is 200, it will be 216 ohm, and if you calculate the current will be coming out to be I by V by Z, which will coming out to be 126 milliamp. ampere. If you calculate it using calculator, you will get this answer. Okay, in COMEDK exam you are allowed to use on-screen calculator, but generally they do not give you a problem where you actually require to solve it. This is one of the exception where you have to use the calculator, because you cannot simply do I by R, V by R to calculate I. Okay, because Z can be much different than resistance based on the given problem. Okay, now next question. A transformer is one of the important concept in COMEDK. Okay, based on transformer a lot of question comes, and the transformers are actually not ideal transformer, very important part. A transformer having efficiency of 90%, that means the transformer is not ideal, and 90% means 10% of the energy is lost. Okay, working on 200 volt and 3 kilowatt power supply. If the current in the secondary coil is 6 ampere, the voltage across the secondary coil and current in the primary coil. So first of all, primary, what is given? Primary voltage and the input power. Okay, input power is given, primary voltage is given. Okay, so we know that input power equals to the primary voltage into primary current. Power equals to VI, Vodafone Idea, power equals to VI. Okay, so this is the most important formula in this chapter. Okay, now power here is given 3 kilowatt. Kilo means 10 to the power of 3. Voltage is given 200. You need to find the primary current. So primary current is 3000 divided by 200. Okay, 3 into 10 to the power of 3 is 3000. So you get 15 ampere. So the input current is 15 ampere. Now if you see that 3 options given here have the same 15 ampere current. Okay, so thus you have to calculate the secondary voltage as well. Now for secondary, how to calculate the power? You cannot take this 3 kilowatt power. If it is an ideal transformer, then the input power equals to output power, so both would have been same. But here it says that the transformer is only 90% efficient. Okay, 90% efficient means whatever power input you have given into 90 divided by 100. This is how the efficiency works. Okay, so 90% efficient means input power into 90 by 100. 10% efficient means input power into 10 by 100. Okay, so here we will be, this is given 3 into 10 to the power of 3 into 0.9. 90 by 100 is 0.9. So that means it will be 2700. Okay, 2700 watt is the output power. Now for output power, what we can write? That it must be equals to output voltage into output current. That is secondary is output, primary is input. Okay, remember in a transformer what happens? This is the input. Okay, input means this is input and this is primary, and this is output, and this is secondary. Okay, output is collected from secondary, input is provided by the power station. Okay, so now that is here is secondary voltage we do not know, secondary current is given 6 ampere. Okay, so that is equals to 2700. So secondary voltage equals to 2700 divided by 6. 6 means 3 2s are 6, 3 9s are 27, so it will be 450. Okay, so 450 volt and 6 ampere. Okay, 450 volt and 15 ampere. 450 volt and 15 ampere is the correct combination. Okay, so 450 volt and 15 ampere is the correct combination. Now let's move on to the next question. Given below are 2 statements. Statement number 1, the reactance of a circuit is 0. It is possible that the circuit contains capacitor and inductor. Reactance means XL minus XC. Reactance means XL minus XC is called total reactance of the circuit. So reactance is 0. Reactance is 0. it is possible the circuit contains L and C. Is it possible? Yes, it is possible. If XL is equals to XC, then the total reactance will be 0. And when it is possible? It is possible at resonance. Okay, it is possible at resonance. At resonance, XL becomes equals to XC. So that means this is a possible. The circuit may contain inductor and capacitor. It may not contain, but it still may contain. In AC circuit, average power delivered by the source never becomes 0. So in AC circuit, if the circuit contains only inductor or only capacitor, the average power delivered by the source is 0. Okay, so if it is only if it involves a resistor, average power dissipated will not be 0. But if it is a pure inductor or pure capacitor, then the average power dissipated will be 0. So this is a wrong statement. This is a wrong statement. Okay, so statement 1 is true, but statement 2 is false. Okay, I think there is some mistake here. You can scratch it. So statement 1 is true, but statement 2 is false. Now let's move on to the next question. An inductance of 200 by pi millihenry, a capacitance of 10 to the power of minus 3 by pi farad, and a resistance of 10 ohm are connected in series with an AC source of 220 volt 50 hertz. The phase angle of the circuit. So phase angle, what is phase angle? What is phase angle? So tan phi is XL minus XC modulus by R. Okay, we take modulus so that sign does not disturb our calculation. So we have to calculate XL. XL is 2 pi F into L. So 2 pi F given here 50 hertz. Okay, and L is given 200 by pi millihenry. Milli means 10 to the power of minus 3. Do not forget that. Milli also you have to consider. Now that is 100 into 200 into 10 to the power of minus 3. 1, 2, 3 zeros. So these 3 zeros are gone. With this cancels. So we get 20. So 20 is XL. What about XC? XC is 1 by 2 pi F into C. So that is 1 by 2 pi into 50 into C here is 10 to the power of minus 3 by pi. Right? So now and given in farad also, so we don't need to consider anything. So pi cancels. 2 into 50 is 100. 2 into 50 is 100. 100 into 10 to the power of minus 3, that is 1 by 10 to the power of minus 1, that is 10. Okay, so 10 and 20. XL is 20, XC is 10. So what is this? So this will be the phase will be, let me write the phase on the other side here. So tan phi equals to 20 minus 10 divided by resistance is 10. So that is 10 by 10. That is 1. So if tan theta is 1, the angle is 45 degrees or pi by 4. So the phase is pi by 4. Okay, easy question, slightly lengthy but solvable. Okay, so this kind of questions are very common, where you have to calculate impedance, phase. Okay, in case of transformers, where you have to solve question based on the efficiency of transformer, right? Now if you want to take admission into our COMEDK test series or COMEDK crash course, where we will be solving more such questions in detail, in depth, okay, then definitely you have to join our crash course. Also the rank booster test series, where you will get the question practice. Okay, 12 full length paper is available for 999 only. And if you want to join our COMEDK crash course, the price of COMEDK crash course is 2499. The classes will start from 6th of April. The classes will start from 6th of April, and the price of the crash course is 2499. So if you are really serious about COMEDK and you really want a good platform from where you can secure a good rank in COMEDK, definitely click on the description of the video and register yourself today. Okay, don't be late. The classes will start from 6th of April. Okay, so be there and prepare with us for a very good rank in your COMEDK. Right, I'll be back with more chapters in future of COMEDK. Till then, bye.